Imagine you're learning to play chess. You could do one of two things. Option 1, you play millions of games, win some, lose some, and slowly, very slowly, your gut tells you which moves feel right. No plan, just instinct honed through brute experience. Option 2, you learn the rules of the game first. You build a mental model of how pieces move, how positions evolve, and then you think ahead. You simulate future moves in your head before you touch a single piece. One of these approaches sounds a lot more like how humans actually learn, and it turns out it's also one of the most exciting frontiers in modern machine learning. Welcome to model-based reinforcement learning. I'm going to take you on a full tour today. We'll cover what it means to learn a world model, how agents use that model to plan or imagine the future, and finally how this whole paradigm stacks up against the more well-known model-free approaches you may have already heard about, things like PPO, SAC, or DQN. By the end of this video, you'll have a solid conceptual and mathematical foundation for MBRL, and you'll understand why it's considered one of the most promising paths towards sample-efficient, general artificial intelligence. Let's dive in. Reinforcement learning, a 90-second refresher. Before we go model-based, let's make sure we're on the same page about reinforcement learning in general. In RL, we have two main characters, an agent and an environment. At every time step, the agent observes the current state of the environment, takes an action, and receives back a reward signal and a new state. The agent's goal is to learn a policy, a mapping from states to actions, that maximizes the cumulative reward over time. We formalize this as a Markov decision process, or MDP. An MDP is defined by 5 things: a state space S, an action space A, a transition function T, a reward function R, and a discount factor gamma. The transition function T tells us, given that I'm in state S and I take action A, what state will I end up in? In the real world, and in most challenging RL problems, we don't know T. The agent has to learn from experience, and that is precisely the fork in the road that separates model-free from model-based RL. Model-free methods learn a policy or value function directly from experience, without ever explicitly building a model of T. Model-based methods say, let's first learn T, the transition dynamics, and then use that learned model to make smarter decisions. Learning a world model. All right, let's talk about the core idea, learning a world model. A world model, sometimes called a dynamics model, is a learned approximation of the environment's transition function. We write it as T hat, T hat. Instead of knowing the true rules of the world, the agent collects experience, sequences of states, actions, and resulting next states, and fits a function approximator, typically a neural network, to predict, if I'm in state S and I take action A, what will happen next? More precisely, we want to learn the following. Notice I said deterministic or probabilistic. This distinction is huge. A deterministic model says, given S and A, here's exactly the next state. Simple. But the world is rarely that clean. A probabilistic model, like a Gaussian model or a full neural network ensemble, outputs a distribution over next states. This lets the model express uncertainty. I think the next state is probably around here, but I'm not sure. Uncertainty awareness is one of the secret weapons of modern MBRL. We'll come back to it. Now, how do we actually build these models in practice? Neural network dynamics models are the most common approach. You feed in the concatenated state and action vector, pass it through several hidden layers, and the output is the predicted next state, or the parameters of a distribution over next states. One incredibly popular variant is the probabilistic ensemble. Instead of training one neural network, you train an ensemble of, say, 5 to 7 networks on different random subsets of your data. Each network gives a slightly different prediction. The disagreement between ensemble members is a direct signal of epistemic uncertainty, uncertainty due to lack of data. Regions of state space that the agent has visited many times will show high agreement. Novel, unexplored regions will show high disagreement. There's another class of world models worth mentioning: latent space models. Instead of modeling the world in raw observation space, which can be extremely high-dimensional if you're working from images, latent space models first encode the observation into a compact latent vector Z, then learn dynamics in that latent space. The idea: the raw pixel space has a ton of irrelevant information. The background of an Atari game, for example, doesn't tell you much about the physics of the ball. A good encoder strips that away and leaves only the causally relevant structure. The most famous modern example of this approach is Dreamer, or Dreamer v3, from Google DeepMind. Dreamer learns a recurrent state space model, or RSSM, that maintains a latent state, transitions through it using learned dynamics, and allows the agent to dream, to imagine thousands of future trajectories entirely inside the model without ever touching the real environment. So let's recap what we've built so far. We have a world model, a neural network, possibly an ensemble, possibly operating in latent space, that has learned to predict the future from data. Think of it as the agent's internal simulator. Now comes the exciting question: what do we actually do with this model? Planning versus learning, MPC and rollouts. Now we hit the heart of model-based RL. Once you have a world model, how do you use it? There are two main philosophies, and they're not mutually exclusive. The first is planning, using the model at decision time to look ahead and pick the best action. The second is learning from imagined experience, using the model offline to generate synthetic rollouts that you train a policy on. Let's take them one at a time. Planning with Model Predictive Control, MPC. Model Predictive Control, or MPC, is a planning strategy that has deep roots in classical control theory. It was used in industrial process control long before deep learning existed. The idea is refreshingly simple. At every time step, you 1. Take your current state. 2. Sample a large batch of candidate action sequences, say sequences of length h, where h is your planning horizon. 3. Roll each candidate sequence through your world model to simulate what would happen. 4. Pick the action sequence with the highest predicted cumulative reward. 5. Execute only the first action of that sequence in the real world. 6. Observe the new real state and repeat the whole process. Why execute only the first action? Because the world model isn't perfect. Errors compound over time. A small mistake at time step 1 gets amplified by time step 10. By replanning at every step with updated real observations, you stay anchored to reality and prevent the agent from drifting deep into model error territory. Now, how do you actually search over candidate action sequences? There are several approaches. The simplest is random shooting. Sample n random action sequences, evaluate each with the model, pick the best. It's dumb but surprisingly effective in lower dimensional spaces. A much better approach is the Cross-Entropy Method, or CEM. CEM maintains a probability distribution, usually a Gaussian, over action sequences. It iteratively, samples a batch of candidates, evaluates them, keeps the top K elite candidates, and refits the Gaussian to those elites. Over several iterations, the distribution collapses around high-reward sequences. This is essentially a derivative-free optimizer, and it works remarkably well. The most powerful approach, if your model is differentiable, is to actually back-propagate gradients through the model to directly optimize the action sequence. You unroll the model for H steps, sum up the rewards, and compute gradients of total reward with respect to the actions. This is sometimes called trajectory optimization, or shooting with gradient descent. Learning from imagined rollouts. The second philosophy is different in spirit. Instead of using the model at decision time to pick actions, we use the model offline to generate a massive amount of synthetic training data that we then use to train a policy with standard model-free algorithms. The key insight: the world model is a cheap simulator. Running the real environment might be expensive, think of a physical robot, or a slow physics simulator. But querying a neural network costs almost nothing. So the agent can generate millions of imagined experience tuples, SARS, entirely inside the model, and train its policy on those. This is the core idea behind algorithms like DINA, one of the oldest and most influential frameworks in MBRL, originally proposed by Rich Sutton. The more modern extension of this idea appears in MBPO, Model-Based Policy Optimization, from Jana et al. MBPO makes a crucial observation. Long model rollouts are dangerous because errors compound. So instead of rolling out for hundreds of steps, MBPO uses very short rollouts, sometimes just 1 or 2 steps, but does them from real states sampled from the replay buffer. Short rollouts stay close to the real data distribution, keeping model error manageable while still providing a significant data augmentation benefit. This is a theme you'll see throughout MBRL. The art is always in managing the trade-off between exploiting the model and trusting it. Pros and cons: MBRL versus model-free RL. All right, we've covered what world models are and how to use them. Now let's step back and ask the big question: when should you actually use MBRL? And when should you stick with model-free methods? This is not a theoretical question. Your answer will completely change your choice of algorithm, your compute budget, and your expected pain points. Let's go through the key dimensions one by one. Advantage 1: sample efficiency. This is the headline advantage, and it's a big one. Model-free algorithms like PPO or SAC typically require millions to tens of millions of environment interactions to solve even moderately complex tasks. That's fine if your environment is a fast video game simulator, but completely impractical for a real robot that takes 10 minutes to reset between episodes, or a drug discovery pipeline where each step costs thousands of dollars. MBRL algorithms routinely achieve 10 times to 100 times better sample efficiency. Dreamer solves many continuous control benchmarks in under 100,000 environment steps. SAC on the same benchmarks needs closer to 1 to 3 million. That's an order of magnitude difference. The reason is simple. The model lets the agent learn from imagined experience. Every real interaction is worth far more because the agent can squeeze 100 virtual transitions out of it. Advantage 2: planning and generalization. Because MBRL agents maintain an explicit model of the world, they can potentially generalize to new tasks with the same model, as long as the underlying dynamics stay the same. Imagine a robot arm that learns a dynamics model from one task, picking up a cup. Now give it a new task, stacking blocks. In a model-free approach, you'd need to retrain largely from scratch. In a model-based approach, the transition dynamics, how the arm moves, how objects respond to forces, are the same. The agent can reuse the world model and just replan for the new reward function. This is the vision of task-agnostic world models. Learn the physics once, plan for arbitrary goals on top. Disadvantage 1. Model bias and compounding errors. Here's the dark side. A world model is never perfect. It's an approximation, and that approximation can go wrong in subtle ways. When a policy is trained entirely on model-generated data, it will eventually find ways to exploit the model's errors, to find action sequences that look great in the model's predictions, but are catastrophically bad in the real world. This is called model exploitation or model bias. Think of it like a student who learns to game a practice exam without understanding the real material. Great scores on mock tests, disaster on the actual exam. This is mathematically captured in a concept called distributional shift. The distribution of states visited under the policy trained on model data starts to diverge from the distribution of states in the real environment. Disadvantage 2. Model learning is hard. Training a good dynamics model is a non-trivial machine learning problem in its own right. In high-dimensional spaces, like raw image observations, or environments with contact-rich physics, the model must capture extremely complex, multimodal transition distributions. Getting this wrong doesn't just mean the model is slightly inaccurate, it means the agent plans against a distorted version of reality, leading to systematically bad behavior. Some specific challenges. Partial observability. What the agent sees might not tell the full story about the state. Discontinuous dynamics. Think of the moment a ball bounces or a robotic gripper makes contact. Stochasticity. Some environments have genuine randomness that deterministic models can't capture. This is a significant engineering and research burden compared to model-free methods, which bypass all of this by just running gradient descent on raw experience. The verdict: when to use which. Let me give you a clean, practical heuristic. Use model-based RL when your environment interactions are expensive or slow, when the underlying dynamics are relatively smooth and predictable, when you need to generalize across tasks with the same physics, or when you want to incorporate prior knowledge about the structure of the world. Use model-free RL when your simulator is fast and cheap, when the environment has complex, high-dimensional, contact-rich or highly stochastic dynamics that are hard to model, when you care more about peak asymptotic performance than about the number of samples needed, or when engineering simplicity is a priority. And increasingly, the research frontier is hybrid approaches. Algorithms like MBPO, TDMPC2, or Dreamer v3 that blend the sample efficiency of MBRL with the asymptotic stability and robustness of model-free policy optimization. Summary. Let's bring it all home. Model-based reinforcement learning is, at its core, about one idea. Don't just learn from experience, learn to understand the world and use that understanding to think ahead. We covered 3 big ideas today. First, learning a world model, fitting a neural network, deterministic or probabilistic, in raw state space or in a learned latent space, to predict how the world transitions in response to actions. Second, using that model, either through planning at decision time, like MPC with random shooting or CEM, or through imagined rollouts that we use to train a policy more data efficiently, like in DINA or MBPO. Third, the honest trade-off. MBRL gives you stunning sample efficiency and opens the door to task generalization, but it comes with real costs, model bias, compounding errors, and significantly higher engineering complexity. The field is moving fast. In 2024 and 2025, models like Dreamer v3 and TDMPC2 have shown that MBRL can match or exceed the performance of model-free giants while using a fraction of the data. And as real-world robotics and autonomous systems demand more from RL, the pressure to be sample efficient is only going to grow. If you want to dive deeper, I'd strongly recommend reading the MBPO paper by Jana et al., the Dreamer v3 paper by Hafner et al., and Rich Sutton's original Dyna paper from 1991, which is remarkably relevant even today. If you found this useful, please subscribe, leave a comment with questions, and check out the linked resources in the description. Next video, we're going to go deep on offline RL, which takes the idea of learning from a fixed dataset to its logical extreme. See you then.